Okay, 11.4, series with positive terms. A quick review of what I covered last class. We talked about the test for divergence. We learned that if we have a series in the form sigma and from 1 to infinity, then if the limit of an, so the general term here, if that limit as n approaches infinity, if that is not zero, or if this limit as n approaches infinity does not exist, so in either of these two cases, the series S diverges. So that's actually the easiest test that you can have for a series. You just look at the general term of the series, you take the limit of that as n approaches infinity, and you see whether you get something other than zero, or you see whether you have a situation where the limit does not exist. If one of these two happens, then you know that the series diverges. But the other thing that can happen is that maybe the limit of an as n approaches infinity is actually equal 0. In that case, the test is inconclusive. So that was one thing we learned last class. Then we looked at the integral test. With the integral test, if you can find a function f of x so that this function is continuous, positive, and decreasing from 1 to infinity. It actually doesn't need to be from 1 to infinity. It could be from any finite number to infinity. So you can say you need a function that is eventually continuous, positive, and decreasing, so that an is equal f of n. In that case, you can calculate the integral from 1 to infinity of f of x dx. It's an improper integral. And if this improper integral is convergent, then so is the series sigma an. And if this integral is divergent, then so is the series sigma an. So that was the integral test. And we looked at a few examples. For example, we looked at this series, we looked at this series, and we learned that this one here is divergent, and this one is convergent. That was example 1 and 2. Now, generally, you can have a situation like this. You can have a series that is defined like sigma 1 over n to the power of p, n from 1 to infinity. And a series that has this form is called a p-series. And we had a theorem that says that if p is greater than 1, then the series is divergent. Then S is, convergent. The moment p is greater than 1, the series is convergent. For any situation where p is less than or equal to 1, then the series is divergent. So, for example, just by looking at the series like this, 1 over, let's say, root n, you can tell that this is divergent, because this is like having sigma 1 over n to the power of 1 over 2. So in this case, p is 1 over 2. 1 over 2 is less than 1, so the series is divergent. Or if you have sigma, let's say 1 over n times root n, then this is like having sigma 1 over n to the power of 3 over 2. Then you can see that this one is convergent, because here p is 3 over 2. 3 over 2 is greater than 1. So this series here would be divergent, and this other series here would be convergent, because these are p series and we had this. So convergence of the p series, if you have a series that has this form, if p is greater than 1, the series is convergent. If P is less than or equal to 1, the series is divergent. So this was that. I'm just going through these quickly because these are the things that I covered last class. And the last thing I want to talk about is the comparison test. So this is new stuff for today. So comparison test has a very, very simple logic. Imagine you have a series like this. Sigma an, let's say n starts from 1 to infinity, and you have another series, sigma bn, n from 1 to infinity. And also imagine that you have this situation. An is less than or equal to bn for any n greater than or equal to 1. That is, for example, A1 is less than or equal to B1. A2 is less than or equal to B2. A3 is less than or equal to B3, and so on. So this is the case for all the terms of this two series. So if you compare the terms of the series one by one, you can see that Bn is always greater than An for any n. Yes? Then just use your logic and tell me the answer to this. What happens if you figure that this series, so what will happen eventually is that when you add up all the ANs, that is sigma AN, that is going to be less than or equal to sigma BN, right? Because if every term of the first series is smaller than the corresponding term of the second series, then when you add up all the terms of the first series, so that you have the first series, and when you add up all the terms of the second series so that you have sigma bn here, then logically that would be the case that sigma an is going to be less than sigma bn. Now, what if I am able to prove that this is a finite number? If I'm able to prove that sigma bn is convergent, in other words, if I'm able to prove that sigma bn equals a finite number, then automatically this one would also be convergent. Does that make sense? That is, if this one is equal a finite number, for example, this is equal 10, and this one is smaller than that, then automatically this one has no choice but to be convergent. That is, it should also be equal some finite number. Now, the other thing that you can conclude here is that if this one, the smaller one, if that diverges to infinity, then this one also has no choice because this is bigger than that. What is bigger than infinity? Infinity, right? So these are the two conclusions you can get from the comparison test. We have the comparison test here. Suppose that sigma an and sigma bn, both of them are series with positive terms. This is something that I forgot to mention, but generally this section is all about series with positive terms. So these A1, B1, A2, B2, A3, B3, all the terms of both series are positive numbers. Then if sigma Bn is convergent and An is less than or equal to Bn for all n, then sigma An is also convergent. So if this one here is convergent, then so is this one. And if sigma Bn is divergent and An is greater than or equal to Bn for all n, then sigma An is also divergent. So the way that I have stated it, it's a little different because I'm assuming that An is less than or equal to Bn. So the way that I said it is, I think it's easier to understand. I would say that if this one is divergent, that is, if the sigma An is infinity, then so is this one. Now notice that in this situation, there are two conclusions, and there are two other things that can happen which would be inconclusive. So I'm going to explain that. So imagine that we have S1, let's say the first series sigma AN, and we have S2, that's the second series BN. And imagine that AN is less than or equal to BN for all n greater or equal 1. Then we can say that in a situation like this, sigma AN would be less than or equal to sigma BN. Then if sigma AN is convergent, if sigma BN is convergent, then so is sigma AN. So that's one thing you can conclude. In other words, if this is finite, then so is this one. If sigma AN is divergent, then so is sigma BN. In other words, if this one here is infinity, since this one is greater than this, then the other one would also be infinity. So if sigma AN is divergent, then so is sigma BN. And now there are two things that can happen which will give you no conclusion. So what if sigma BN is divergent? So what if you know that, for example, this one here is infinity? If this one is infinity, then you know nothing about this one. This could be infinity, or this could be a finite number. Make sense? So if sigma BN is divergent, then you know nothing about sigma AN. That is, comparison test will not work in this situation. The other scenario, what if sigma AN is convergent? If the smaller one is convergent, so imagine that this is a finite number. For example, this is equal 10. If this is equal 10, then what do you know about sigma BN? You know nothing, yes? It could be finite, it could be infinite. So if sigma AN is convergent, then you know nothing about sigma BN. So the theorem actually covers these two, because the other two are actually inconclusive. They're useless. But if you're able to find a series Bn that is convergent, then you can also conclude that sigma AN is convergent. Or if you're able to find a series AN that is divergent, then you can also conclude that sigma BN is also divergent. So to make things more clear, I'm going to give you a few examples. So you want to determine whether sigma 1 over n squared plus 2, sigma 1 over n squared plus 2, n from 1 to infinity, you want to know whether this is convergent or divergent. So by looking at this, you can see that this should remind you of the p-series sigma 1 over n squared, n from 1 to infinity. Just think about those dominant terms. On top you have a 1. It's the same for both of them. At the bottom you have n squared plus 2, but plus 2 is not the dominant term. So the term that really matters is n squared. So you can compare these two. Do you agree that 1 over n squared plus 2 is less than or equal to 1 over n squared? And the reason for that is they're the same, except for this one has a bigger denominator. So for any n greater than or equal to 1, sigma 1 over n squared plus 2 is going to be less than or equal to 1 over n squared. Okay, then what does that mean? That means sigma 1 over n squared plus 2 is also going to be less than sigma 1 over n squared. Now this one here is a p-series, which is convergent. So we can say since 1 over n squared is a convergent p-series, then so is sigma 1 over n squared plus 2 by the comparison test. So this is how you're supposed to answer a problem like this. You're supposed to find another series that is familiar, another series that you know whether it's convergent or divergent. It could be a p-series, it could be a geometric series, because for a p-series or a geometric series, in most cases p-series, you can just tell by looking at p, you can tell whether it's convergent or divergent. You can just look at 2 here, that's the p, it is the convergent. So you can now use the comparison test. Any questions? Another example. Sigma 1 over 3 plus 2 to the power of n, n from 1 to infinity. Okay, so let's say this is our sigma an. Yeah, then we can define sigma bn to be sigma 1 over n squared, n from 1 to infinity. How does this help? This is like having sigma 1 over 2 to the power of n, n from 1 to infinity. And we know that this series here is a geometric series, and the common ratio is 1 over 2. So it's between -1 and 1. That makes it convergent. Now, let's compare an and bn. 1 over 2 to the power of n plus 3 is less than or equal to 1 over 2 to the power of n for any n greater than or equal to 1. Why is that? Because they're all the same except for this one has a bigger denominator. Bigger denominator means a smaller fraction. So for any n, the corresponding terms of the series of interest, they're less than the series that we defined. That means the sum would also be smaller. So this series here would be smaller than this series. And since sigma 1 over 2 to the power of n is a convergent geometric series or G series, then so is sigma 1 over 2 to the power of n plus 3 by the comparison test. Are we good? Any questions? Next example. Sigma 1 over root n minus 1, n from 2 to infinity. Okay, so the series that I need to create for the comparison again is, just think about the dominant term. That minus 1 here doesn't matter. So I would have to compare this with 1 over root n, and 1 over root n is a p series where p is 1 over 2. So it is going to be divergent, because for any situation where p is less than or equal to 1, the P series is going to be divergent. So this one here is divergent. Now, I would be able to use the comparison test if every term here is greater than every term here. Is that the case? 1 over root n minus 1. Is it greater than or equal to 1 over root n for any n greater than or equal to 2? Yes, it is. Why? Because this one here has a smaller denominator. A smaller denominator means bigger fraction. Yes? So for any n greater than or equal to 2, this fraction here with a smaller denominator will be bigger. So sigma 1 over root n and sigma 1 over root n minus 1, when you compare these two, this is bigger. And this other series here is a P series that we can tell is divergent. So by the comparison test, the series of interest is also divergent. So you can say, since sigma 1 over root n is divergent, then so is sigma 1 over root n minus 1 by the comparison test. Any questions? Okay, so imagine, I just want to give you a situation where the comparison test would be inconclusive. Imagine you have something like this. You have sigma 1 over root n plus 1, yes, and from 2 to infinity. And you may say, okay, this reminds me of the P series 1 over root n. And this one here is divergent. So if these elements are bigger than these elements, then I can use the comparison test. Let's try. I have 1 over root n plus 1. I have 1 over root n. And when I compare these two, I can see that this is the case. That 1 over root n is greater than 1 over root n plus 1, because here I have a bigger denominator. Bigger denominator, a smaller fraction. So for any n greater than or equal to 2, that's the case. Now, I know that this one here, so this means sigma 1 over root n and sigma 1 over root n plus 1, this one is going to be a smaller. Now, I know that this is divergent, so this one is divergent. Then what do I know about this one? Nothing. Yes, could be divergent, could be convergent, because if this one is infinity, then this one could be infinity, or it could be some finite number. So in that case, the comparison test would be inconclusive. Comparison test is inconclusive for this problem. There are other tests, but we're not going to cover them. So you don't need to worry about a situation like this, because there is another test called the limit comparison test, which is not part of your course. You would use that test in a situation like this. So you can be sure that if in the test, in the final exam, if you get something, a series, either it's a P series or a geometric series or a telescoping series, or if it's not one of these situations, you would be able to use the comparison test, like these three examples that we looked at them here. Yes, for each one of them, you were able to use the comparison test, and for none of them, the comparison test was inconclusive. So a situation like this, you don't need to worry about it much. Any questions? Okay, so that's the end of section 11.4. I'm gonna stay here for a while to answer your questions.